Good morning, everyone. In previous class, we have seen the maximum torque equation, which is equation 5.14. And this maximum torque is independent of slip. We have made this equation 514 as independent of slip. And also it is independent of rotor resistance. You can see there is no rotor resistance term here. So the maximum torque equation is independent of rotor resistance and independent of slip. And this maximum torque equation is also known as breakdown torque. This maximum torque equation is also known as the breakdown torque. Okay, using this equation, we can plot different characteristics. For example, speed torque characteristics, and we can also plot the speed current characteristics also. Here I have shown two different type of characteristics. See, this is general speed torque characteristic and speed current characteristic. This is speed current characteristic and this is speed torque characteristic curve. And the second figure, which is figure 5.3, is the variable voltage characteristics between the speed and torque with respect to different voltages. Now let's discuss about this first figure, which is speed torque and speed current characteristics. Both the rotor current, which is IR, and the torque T are zero at synchronous speed. See, this is the synchronous speed point. You can observe both are at zero position at the synchronous speed. When the speed is going to decrease, then the rotor current as well as the torque both are increasing. You can see both the curves are increasing, but the speed is coming down here. So the speed is coming down, but the rotor current as well as the torque both are increasing, continue to increase. And you can see this rotor current, it will continuously increase until the speed reaches to zero. So at this point the speed is zero. You can see the speed is slowly decreasing and comes to zero. And at this point, when the speed is zero, the rotor current reaches at its maximum point. But coming to this torque curve, you can see until some point, this point is also known as breakdown point. This region is a breakdown region, and I hope this is the maximum point or the maximum torque value. Up to this point, the torque is increasing with respect to the speed. If the speed is reducing, then torque is increasing this way. Torque is increasing this way until it reaches to the breakdown point, or we can say maximum torque value. At this point, at this dot, the torque will be at its maximum value. After this point, means after the maximum or the break-even point, the torque also starts decreasing its value. You can say at this point, let us say this is the x-axis value. Suppose it may be 10 Newton meter. At this point, the torque is 10 Newton meter. After that point, the torque is also started decreasing with the decrease in speed. So the speed is gradually decreasing, and you can observe the torque is also decreasing. Suppose let us take at this point, you can see here at this point the torque is maybe around 8 Newton meter. So it is decreasing. Previously it is 10 at the break-even point or breakdown point. After that it is coming down. At this point the speed is let us say around 1000 rpm, and at this point you can check the speed. It is around let us say it is around 700 or 800 rpm. Means the speed is decreasing, here torque is also decreasing. So after this break-even point or breakdown point, the torque also decreases with respect to the speed. So it will comes to a point where the speed becomes zero. So you can observe the relation between speed and torque up to the maximum point or maximum torque. The torque will increase. When the speed is decreasing, the torque is increasing up to this point. But from this point, which means inversely proportional. So torque and speed both are inversely proportional until the torque reaches its maximum point. So during this portion, torque and speed both are inversely proportional. That means the torque is increasing, but the speed is decreasing. After this point, where after reaching the maximum torque point, the torque and speed both are showing proportionality. Means during this region, the green color marked region, during this region you can see the speed decreases and the torque also decreases. So the characteristic between speed and torque is divided into two portions. The first portion, both are showing inversely relationship. In the second portion, which is a green marked portion, both are showing linear relationship, because speed is also decreasing in this portion and the torque is also decreasing. So here both are in linear relationship. In this region, both are inversely proportional. This is the advantage of induction motor. This is a great advantage that can be added in the induction motor. So because of this nature, many applications needed different conditions. So because of this nature, induction motor is suitable for many of the applications we will see in the next few minutes. But here one thing we need to observe, that the rotor resistance will, which is RR, plays a major role in the decrement of the speed or decrease in the speed. If this rotor resistance drop is very low, then the speed is almost constant. That means the motor operates in the constant speed region. Okay, if this rotor resistance is high, then the speed drop is also very much high. So the speed drops very quickly. Okay, so this speed torque characteristic curve, what we have seen here, this speed torque characteristic curve, this nature of the curve is used to see the variable voltage characteristics. Here the same speed torque characteristic curves are plotted here with respect to different voltages, V1, V2, V3, V4. See, V1 is the highest amount of voltage, V4 is the lowest amount of voltage. V1 magnitude is always greater than V4. So V1 is greater than V2, V2 is greater than V3, V3 is greater than V4. So that means V4 value is very low, V1 value is very high. We already seen that the torque is directly proportional to the square of the stator voltage. From equation 514, we have seen this relationship. The torque is directly proportional to the square of stator voltage, or V. Therefore, as the voltage is reduced, then the speed is also reduced. You can see V1 is highest voltage, V4 is lowest voltage. Then if you reduce the voltage to reduce the speed, for the same current of the motor, which develops a lower torque because the voltage is reducing. So that means the torque production here, you can see the maximum torque will appear at this point for V4, for V3 this point, for V2 and this point, and for V1 this point. You can see if you decrease the voltage, then the torque value will also decrease. If the voltage is low, then the maximum torque will be low. If the voltage is high, then the maximum torque will be high. So this characteristic is very much suitable for the applications where the torque demand reduces with the speed. Means if we want to reduce the speed, then torque also comes down. But we know torque and speed will always have, generally will always have inversely relationship, which means if we decrease the speed, then the torque will increase. Because from the power relationship, P is equal to omega T. So omega is the speed and T is the torque. So if the power is constant, if we make power constant, then P by omega will be the torque. If power is constant, then this relationship shows the torque and speed will have inversely relation. So inversely relationship. Okay. But during the maximum torque point, both are showing linear relationships as discussed here. That means this type of characteristic is very much suitable where the torque reduces with the speed demand, which means the speed and torque both are reducing. In those applications also, induction motor is very much suitable. For example, fan and pump drives are the best examples. If we decrease the speed, then the torque of the fan also decreases. If you regulate the speed, then the torque also will be regulated, which means if you want to decrease the speed of the fan, then fan produces less torque. If the speed is high, fan produces high torque. So in these applications also, these type of induction motors are very much useful because of these characteristics. Okay, so this is about variable voltage characteristics and speed torque characteristics and speed current characteristics. Speed versus rotor current, which is IR. And we have already seen the power equations, which is I think 5.8, equation 5.8. We have seen the power equation right here. We have seen the maximum power equation that is developed at the rotor of the motor. So this power equation we have calculated only by considering the rotor copper loss. Only by considering the rotor copper loss, we have calculated this power equation. So using the same equation, which is equation 5.8, I want to determine the efficiency of the motor. So for that, I'm taking the same equation 5.8 and neglecting all other losses. All other losses means stator copper loss, core losses, other friction and windage losses. All these losses are I'm neglecting. See here, this I'm neglecting stator copper loss, but in the previous section we have considered rotor copper loss. That's why I have shown equation 8 once again. So I'm neglecting all these losses, only considering the rotor copper loss. So that means from equation 5.8, this is the power equation from 5.8. Okay. In this equation, we can replace this term as PG. This term as PG, since from equation 5.6, PG is 3 into IR dash square into RR dash by S. Let us see. See, you can see here the PG, which is the power transferred from stator part to the rotor part. This is PG. So From this equation, this entire term I have replaced with small pg. And here also you can see only rotor copper losses only I have considered. So total power minus rotor copper losses I have uh, made to make the total power developed in the rotor. Other losses are neglected. The same condition I have taken here to estimate the efficiency. All other losses are neglected except rotor copper loss. So using the same 5.8 equation, in this equation, I am replacing this term with PG, because PG is, we know from equation 5.6. So, but we know the efficiency, the motor efficiency is output by input power. So motor output power is the generated power, which is the actual power on the motor, developed power on the motor, which is PM. And the input power of the motor is the power that is transferred from the stator to rotor, which is PG. So from this equation, PM by PG, just bring this PG this side, then PM by PG will be the efficiency. That means efficiency will be eta is equal to 1 minus S, where S is the slip of the machine. S is the slip. So from this equation 515, we can clearly say that the efficiency of the induction motor definitely depends upon the slip. Definitely the efficiency depends upon the slip of the induction machine, but the slip is not constant. Slip will always continuously change. Because of the speed, the slip will also change. So by reducing the stator voltage, the speed of the induction motor can be reduced, which increases the slip. So if the slip is increasing, that means the entire efficiency of the motor decreases. The reduction of stator voltage is possible when some of the power is wasted on the rotor part. So some of the power is wasted on the rotor part, which means the efficiency is decreased due to the loss that is happened on the rotor part. That is because of rotor resistance. That leads to overheating the rotor. If the rotor loss is increasing, means resistance will convert its energy into heat. So that means the rotor part will be overheated. So finally, the speed control of induction motor with stator voltage control produces a reduced efficiency. So from this equation, we simply say that variable voltage equation, or the variable voltage stator voltage control of an induction motor produces with a reduced efficiency. And not only that, it also overheats the rotor, because losses are increased on the rotor resistance. So because of the losses, overheat will be produced in the rotor. Due to these disadvantages, the rotor uh, means this method of speed control, means the variable stator voltage control of speed control, is only suitable for limited number of applications where the power rating is low and the speed is also low. And this type of speed controlling technique is used to vary the speed from 0 to base speed only. So 0 to the base speed or the rated speed of the machine. So from 0 to the rated speed of the machine, we use this type of control. and the applications where the low power applications are there, or the low power rating applications are there, in those applications only we will use this type of variable voltage technique. However, the variable voltage previously performed by different conventional methods. Now the speed control of induction motor, which means the variable voltage technique, is developed with the help of AC voltage controllers. So now, using the AC voltage controllers, we can control the speed of the induction motor effectively. The efficiency of using power electronics, the efficiency of the entire system will also be increased because of the advantages that we have with the power electronic converters. Okay. Now you can see here I am going to show a few different circuits of induction motor with three-phase and single-phase circuits. All these are three-phase and single-phase circuits with different possible combinations of AC voltage controllers. Let's see here, star-connected controller and load. See, this is a three-phase supply, which means we are using a three-phase induction motor. This three-phase induction motor, the stator winding, you can see here, the stator winding is a star-connected winding. In three phase we will have two different type of connections, star connection as well as the delta connection. Star connection as well as a delta connection. So this first figure shows the star connected winding along with star connected AC voltage controller. So this controller is also star connected because each winding will have a series connected AC voltage block. You can see here. See, this is for this winding, and this is for this winding, and this is for this winding. That means the AC voltage controller is a star connected one, and the stator winding is also a star connected one. That means star connected AC controller, AC voltage controller. And the load is nothing but the induction motor here, which is the stator winding of the induction motor. So the stator winding are also star connected. So this is the first combination. Similarly, we can check the star connected controller with the delta connected load. See, the winding, stator winding is delta connected, but you can see the load, sorry, the AC voltage controller is star connected. See, for each and every phase, a combination of controller is placed. But the stator winding is delta connected. So that means star connected controller with the delta connected load. And not only these two, you can see this figure number C, which is a delta connected AC voltage controller with the delta connected load. You can observe here R phase, Y phase, and B phase, but you can see these are stator windings. So stator windings are connected in the delta connection, and similarly, these are AC voltage controlling modules. So these are also connected in delta connection. So this figure indicates the delta connected AC voltage controller with delta connected load. This is also one of the combinations. And the fourth combination is star connected controller and load is neutral. Here a neutral wire is also added, which means three phase four wire system, you can say. So the load is a star connected with a neutral wire, and the AC voltage controller is also a star connected. So for three phase systems, we have star and delta connection. So we have different possible combinations. So A, B, C, D, all four figures are different combinations of different connections that we can made with induction motor using AC voltage controllers. Okay, and this last figure shows the single phase induction motor connection. You can see this is a single phase AC voltage controller, and we can use a triac here or two thyristors. In the place of a track, we can use two thyristors, or a track is enough. And a single phase induction motor is connected here. So this the circuit diagram is for single phase induction motor, and previous four type of connections, these four combinations are for three phase AC voltage controllers fed induction motors. Okay. Okay, in the next class, we will see the detailed operation of AC voltage controller fed three-phase induction motor, and along with the advantages and disadvantages of AC voltage controllers. Means in order to control the stator voltage, how much the AC voltage controllers are effective, which means the advantages of stator voltage controller, and the disadvantages. We will see in the next class. Okay. Thank you.